All right, so notes for section 6.5. We're going to be talking about reaction diagrams, and we're going to talk about what happened yesterday in the lab, right? And how we can represent the energy change in a chemical reaction. Okay, so how does that relate to yesterday? What did we do yesterday? Anybody here yesterday? Yeah. Just me? What did we do yesterday?
We mixed certain chemicals in a compound and either got hot or cold.
Yeah, so we mixed compounds together, and the process of that made that either hot or cold, right? So it was basically a liquid and a compound, water and some compound together, and we made hot packs or we made cold packs, right? The one I demoed here made something so cold it froze ice to a block of wood that was covered in water, and we were able to lift it up with that. All right, so to review what we did yesterday. So this, so here is a fantastic diagram of what we did yesterday, illustrated. I'm there on the left. No, believe it or not, that artwork there is beyond my current ability.
That was you in high school, though.
True, yes. I didn't really part down the middle like that, but close enough. I did have some really awesome blue pants. So this is what we did. Some of these ended up cold. Some of them ended up warm. So let's, come on. That's not what we want to do. Here we go. All right, you're going to want to draw this in your notes, this diagram. And there's going to be two of these. This one is the endothermic change. So your art skill aside, just make sure in your notes that your drawing represents that the energy of reactants, that first little line coming in on the left, is lower than the energy of the products. And we're going to talk about what that means here in just a second. Things together. So yesterday, which of the four reactions, and most of you should have these right there in your notes, did we determine were endothermic? Which ones? The ice pack, I think that was number one, right? Wasn't the ice pack number one?
Yeah.
And then the other one that got cold was the demo, right? Number three. That's where we kind of froze the block of wood to the flask and lifted it up. What does it mean for something to be cold? For us to identify something as cold. Obviously that cold pack is what we're talking about here. What does that mean? This morning when you left for school, you walked out to your car, stood in line for the bus, whatever it was you did, it was cold out this morning, right? What does cold mean? When we feel cold, what are we talking about? Okay, so less than room temperature, sure. Colder than you, what do you mean by that?
If your body temperature is like 70 degrees, anything below that.
Your body temperature is 70? You should see a doctor, bro. Like immediately somebody call for an ambulance. BK is in hypothermia at 70 degrees. Loss of heat. When you feel cold, when you go outside this morning, on your way to school, it was 20-something, I think, this morning. Maybe 30-something. That's cold. We say the word cold. Ooh, it's cold outside. But what that means is we are losing heat to the environment. We are the system. When we think of ourselves and the temperature of our bodies, that's the system. And when it's cold out, our system is losing heat. Right? The cold air is sapping away our heat energy. Right? And so to prevent that, we wear bulky clothes, right? Or we, shake our arms or our hands to try and warm them up. Right? But ultimately, that's what we think of as cold, is simply our body giving away heat. So the ice pack yesterday, that we felt it as cold, right? Cold things take heat away from us. They pull heat into themselves. So in this case, the ice pack was pulling heat, right? We start with an energy of reactants down here, and we end up with more energy. The products have more energy. Where did they get that energy from? The heat of whatever, the surrounding environment. When we poured water into that Ziploc bag, yes, it was out of the sink, so it wasn't necessarily hot water, but it was just lukewarm water, whatever, right? But then when you added it to that chemical, what happened to the temperature? It dropped even lower. It got colder and colder. That chemical process was taking heat energy away from the water. In the case of experiment 3, where I froze that thing to the wood block, same thing. Where did those chemicals get that energy from for that reaction? Where does the energy come from? In the flask, in the wood block. Some of the air, but mostly where? Yeah, the wood and the water, right? That's what froze it solid. This is all about the direction of energy. And where you see this Q system and Q surroundings, right? The system is the reaction, the reactants themselves. Right? And so for them to end up with extra energy at the end, right? They must have gotten it from somewhere. Right? In the case where you were holding on to that ice pack, it literally was taking heat out of your body and going into that chemical reaction. That was what we feel is cold. Right? This little hump here, what do you think of that? What does that mean, activation energy?
That's where it starts to create.
So that's kind of the kickstart of the reaction. Right? And sometimes the kickstart of a reaction can be like a physical shaking of something, like where we were mixing the chemicals together in the bag. Or just the action of the water molecules, the energy of those slamming into those things and making a reaction happen. Typically there's some kind of kickstart process, and that's activation energy. That is measured from the initial energy of the reactants to whatever the peak is of that hump. And then lastly, the overall change in energy, that's this delta H down here. That's the amount of energy that reaction needed to happen. The amount of energy that it absorbed into that process. Right? And if you want what really is happening, right? When you have a chemical reaction, you have something on the left, right? We have our reactants on the left of a reaction. And we have products on the right. And typically there's something different in there, right? We rearrange those things. Those are all chemical bonds that need to be broken, right? And typically you need some kind of energy to break bonds apart. And then when those bonds reformed, they either need energy or they give off energy. And in this case, overall, they needed more energy than they gave off. No? No? Same drawing, but different. You guys did such a great job on your first drawing. We're going to do another one. Now again, this looks almost the same. It has all of the same labels. Energy of reactants, activation energy, energy of products, it's all there. But the shape is significantly different. And in this case, you start on the left higher, and you end up on the right with less energy on your product side. But you still have that bump in the middle. And this is exothermic chemical processes. So here we have an exothermic reaction and the diagram. We start with the energy on the left, and we end up with less energy. So let's think about how that means, or how that works. So let's think of combustion reactions, because those are kind of the easiest example of exothermic processes, right? Where energy is given off. When you burn a campfire or whatever, right, it releases heat and light energy. You can stand there and you can get warmed up from it. And again, just like this morning, when it was cold, you were giving off heat. If you stand in front of a fireplace or campfire or whatever, you feel that heat, right? It warms up your hands. You can feel that radiation. That's all energy. That's heat energy leaving that system, right? In the case of a campfire, are you the system or are you the surroundings if we're talking about a campfire? Yeah, we're the surroundings in that case, right? That campfire is giving off energy, right? That firewood has some amount of energy. And as you burn it, it ends up with much less energy on the other end. That is released as heat and light. And we can feel that. Your delta H here is negative. Why do we say that's negative? What do you mean a fire has negative energy? That doesn't make sense. It feels hot.
It's giving it off the fuel source.
Yeah, because it's giving it off. Fuel source is a great point, right? Your cars, the fuel in your car, in your gas tank, your car has a lot of built up energy. That gasoline has a bunch of stored chemical potential energy, right? And when you light it on fire or explode it in your car's pistons, I guess, right? That gives off that energy, and then the products themselves then have less energy. You've utilized that to drive to school this morning, for lack of a better way to put it. This is where energy flows out of the system. So let's think about this. What kind of process, endothermic or exothermic, is an ice cube melting? An ice cube melting is exothermic.
No.
Henry says no.
It has to gain energy to melt.
Ah.
Energy flowing in or without it.
The ice cube is the system. To get it to melt, do we have to add energy to that system, or is energy leaving the system?
It adds energy to it.
To add energy. Which of these two is adding energy into a system?
Endothermic.
Endothermic.
Okay, Nico.
Phase changes. Think about what's happening in a phase change from the perspective of the stuff itself. Right? And this is where you can have confusion. Because you're like, well, you have to heat up an ice cube to get it to melt, right? Heating things up. That sounds exothermic. No. You have to think of what is the system and what is the surroundings. And if we're talking about an ice cube melting, the ice cube itself is the system. Now, to your point, the surroundings, we need to lose some energy to do that. But the ice cube itself has to gain energy. Melting would be an endothermic process. Same thing with vaporizing, right? Boiling. The process of a phase change is either endothermic or exothermic. Freezing would be the opposite. Again, this is one of those things you really kind of have to think about. Freezing, that sounds cold. Cold seems to me that it should be endothermic. No. From the perspective of the lake, when it freezes, the reason it freezes is because it gave off enough heat energy that now it could form into a solid. So think of the direction, and again, when we're thinking about phase changes, the point of view here, right, the perspective that you need to think about is from the perspective of whatever the substance is. That is either freezing or melting or condensing or vaporizing or whatever.